Hello, everyone. It's really good to have you here today for our live discussion with Dr. Tubana. So welcome to our live. We have 5 people here right now. I would like to ask you to share this video and the link on your Facebook page. And if it is possible to send to some friend of yours, would be really great. I appreciate that, okay? So we're just going to wait a little bit for more people to join our live, and then I invite Dr. Tubana to be a part of it, okay? If you have a question during the live, you can send a message or comment to us, and at the end, we'll open for 10 minutes for questions, all right? So please share with your friends. We're just gonna wait 2 minutes and then we're gonna start, okay? Okay, guys, let's start. Dr. Tubana, she's a professor in the Department of School of Plant, Environmental, and Soil Sciences at the Louisiana State University. She has a PhD in Soil Science and Soil Fertility from Oklahoma State University, Master degree in Soil Science and Soil Fertility, Bachelor degree in Agriculture from University of the Philippines. She has more than 50 articles and around 150 abstracts published, and also had advised more than 80 students, including a postdoctoral fellow, graduate students, visiting scholars like me, and interns. Her research areas are nutrient recycling, fertilization to improve nutrient use efficiency by crops, silicon in agriculture, data in soil fertilization guidelines for Louisiana, nitrogen management, and the use of cover crop, among some others. Now, on the behalf of the Silicon Research Group in Agriculture and Federal University of Uberlândia, I would like to invite Dr. Tubana to start her presentation today. Dr. Tubana will have 20 to 30 minutes, and after we will open for questions, okay? So, Dr. Tubana, welcome to our live. Let's see if the people can see you. Okay, you are with us right now. Can you hear me, Dr. Tubana?
Oh, I can hear you well.
Yes, you are on the live right now.
All right. Good afternoon, everyone. It's a pleasure to be part of the live discussion with the group of, we call it GPSi, right? I know SI, silicon.
Yes. Okay, so I'm sharing your presentation and the live is yours.
All right, thank you very much, Bruno. I heard your introduction. I'm very happy mentioning all those accomplishments that without my grad students and the people who work with me like you would not be possible. So this is one of the things that I like to do a lot, to share the research that we've been doing. And this is just one of the areas that we focus on. And I think this is very timely, especially if we have a host coming from Brazil who's a very well known for sugarcane production. So my topic for today is I'm going to share to you the nitrogen fertilization and sugarcane production here in Louisiana using remote sensor and variable rate applicators. So let me begin my presentation just to give you an idea of our background on sugarcane production in Louisiana. It's actually one of this industry that contribute a lot in our economy. Annually, it has an estimated about $2 billion contribution in the United States. If you look at the country, it is one of the few states that produce sugarcane, and it is the largest. It has the largest production area. Excuse me, with that, one of the largest production areas, about 200,000 hectares, or a little over 400,000 acres. In Louisiana, you can see that area is divided into different parishes, and those shaded areas are the places where we grow sugarcane in the region. And you can see that we have also the state is divided into two climate regions, what we call the temperate and the subtropical climate, where you see the southern part of Louisiana. That's where we produce a lot of sugarcane. Those a couple of parishes where we can say this is the farthest it can go north of the latitude. That's where we also produce sugarcane. There's several acreage right now that we cultivate for production of sugarcane. Essentially, our industry here is relying a lot on varietal diversification. So just to make sure we be able to manage all this problem that we encounter in pests and diseases. If most of you know already, Louisiana is in a relatively warm climate region in the United States, and so you can see we have high pressure of diseases here. And given the fact that there's a lot of varieties that comes out every 10 years or so, or even less than 10 years, you can imagine how much work that we have to do when it comes to fertilizer nitrogen recommendation. It has to be up to date, and with changes of variety or cultivars that we use, that also calls for an up-to-date validation program for nitrogen fertilizer recommendation. Our production level is basically influenced by cultural management practices that we employ here, whether you're doing a crop rotation with beans or having a fallow period at the end of the cropping cycle, or if you practice other conservation tillage practice that involves, for example, residue management and some other practices that will result to improve productivity. And also, it depends on where you're located at, whether your field is under a good soil type. And usually we have this very diverse soil type. And I'll talk about more on that later when we go to these production areas here in Louisiana. So essentially, our production level is dictated by these factors. So the next thing in question perhaps maybe is why nitrogen? This is the most studied nutrients of all the 17 essential nutrients or 14 essential nutrients that are taken up by plant from the soil. So why nitrogen? This is one of the nutrients that is taken in the highest amount by crops, by most crops, excuse me. And looking into that, why is that so? When it comes to function, nitrogen, you see one nitrogen in every unit of amino acid, at least one. And these amino acids, when they cluster and form big clusters of amino acid, it produces proteins and enzymes. So as a plant grows up, it builds up and accumulates nitrogen in it. And so another thing too that you will know about nitrogen is it's a component of these chlorophyll pigments. And if you see the pictures on the right side of the slide, you see those green color chloroplasts. And so there contains a lot of chlorophyll that gives this green color. So essentially, as the crop grows, it accumulates nitrogen, and it is actually constituting about 5% of plant dry matter on average. So that's the highest amount. So that makes it the most demanding nutrient of all the essential nutrients. The next one in line is when you talk about nitrogen, I always associate that being a dynamic and leaky cycle nutrient. And so if you look at this image here, it's a little bit busy, but I'm going to walk you through how we kind of summarize the thought for the information about this slides. And as you can see, the form taken up by plant for nitrogen is ammonium and nitrate. And in the soil, there's way by which it can be added for example, so if you see those arrows pointing towards the the soil. That means it's an addition, a process that you can add nitrogen to the soil. So you can do it by fertilization, deposition by rainfall and dust, which is quite difficult to account. And there's also nitrogen from previous legume crops. And so soil has also organic matter. And upon mineralization process, it releases also this plant available nitrogen form that plant can use up. Those things that makes it what you call leaky cycle. And if you notice those red boxes, those are the pathways by which nitrogen can be lost from the soil system. Let's begin with what we call this ammonia volatilization. And so in each of those boxes, you'll see the number of, or the estimated amount of nitrogen in pounds per acre per year that can be lost from that particular process alone. So with ammonia volatilization, that can take place in high soil pH, and especially if it's a dry condition, almost as much as 45 pounds of nitrogen per acre is lost. Now, even if it's taken up by plant, as shown in that very, let me see if I can use a pointer here. So this process here, where plant takes up nitrogen, it is not a guarantee that nitrogen will not be lost if it's inside the plant already. Through the process, reduction process, from which inorganic N is converted into organic form, that sequential process results in the formation of the gaseous form of nitrogen, by which nitrogen can be lost through volatilization as well. And you can see it's as much as 70 pounds of nitrogen per acre. In the soil where we have a lot of rainfall, a good example here, Louisiana, nitrogen can be lost, especially that form of nitrate, by leaching. And if in case rainfall exceeded infiltration, and so runoff start taking place, and that where we have also losses of nitrogen, including the sediments. Going back to leaching, amount of losses that we can expect is about 30 pounds per acre, more than that per year, and that's a substantial amount as well of nitrogen losses. And plus, of course, the threat that it will impose to the quality of water in a nearby location. The last one is what we call the nitrification process. This is by which, when nitrate is acted upon by microorganism and further reduced to form this gaseous form, and so that denitrification takes place. And so you can see this image alone is very dynamic, and definitely the nitrogen cycle is very leaky. That losses alone can be equivalent to many $1 million of money in the form of losses from the fertilizer that we applied, and at the same time the environmental consequences that it may impose. Another thing too that would like to emphasize is that because it's the demand for nitrogen is quite high, it is the nutrient that is always applied in the highest amount, and with the price of fertilizer being is essentially increasing with time. And you can see here the diagram here, we have that on the y-axis you have the dollars per short ton material, and on the x-axis you have that years, and you can see that there's no point of going down, it's just continuously increasing. And so that means investment involved for fertilizer nitrogen is also increasing. Another thing too that is quite important why we studied nitrogen is the associated cost when we mismanagement nitrogen. It's very costly to the environment. So for those who've seen this diagram, this is an image of this is a figure of a photo of United States, and this area here that is highlighted, these are the Mississippi River Basin. It actually where most of about 21 states and 2 Canadian provinces are actually contributing or using Mississippi River as the basin. So this non-point source of pollution or nitrogen are actually going to the Mississippi River, and that caused this enrichment in the Gulf of Mexico. And so that caused this what we call dead zone, which actually interrupts this marine ecosystem. And year to year, the area or of the dead zone changes, and there was a year, probably 2 years ago, that it hits the highest, about 7,000 miles squared. So that's another problem associated with mismanagement of nitrogen, in addition to losses of investment. And when we talk about more of global nitrogen, mismanagement of nitrogen can also cause an issue with regards to global warming. And so this graph here, where you have Erisman showing the potential usage of nitrogen fertilizer up to uh, 2100, that's year 2100. Different models predicting how much nitrogen will be produced. Regardless, what it shows there is that with that amount that we produce, that also increases the amount of atmospheric nitrous oxide deposition. And so if you look at the greenhouse gases that trap heat, and you have here a diagram showing all those greenhouse gases, a study by Forster in 2007 showed that among these greenhouse gases included nitrous oxide that increases from year 1750 to 2005. It's not as high concentration as carbon dioxide, but the fact it's increasing, and considering the global warming potential equivalent to about 100 years it stays there in the atmosphere, it's about 300 times higher global warming potential as the carbon dioxide. So it's something that is quite significant when you look at, you break it down to its potential, and its it stays there being for a long time in the atmosphere. So that's why we studied nitrogen, and there's no exception about with our crop production here in Louisiana. Just to give you an idea of what type of soil that we cultivate, and you can see that area here where you outline the brown area here. This is the Mississippi River alluvial plain here, where you have most of this relatively young soils rising from this deposition from flooding that took place for 100 years. Relatively, the soil is young, geologically speaking. And when you talk about geologically speaking, it's 100, 500,000 years younger. So we have several of this area here. And where you have the sugarcane production region is this area in the southeast Louisiana. And when you say diverse soil, this is a good example, a very good example of what I'm talking about when you're dealing with the soil on the alluvial plain. So this is the Mississippi River. And with that, you can see where we have this sugar research station here, the LSU Ag Center Sugar Research Station. And so the soil type, as it goes closer to the levee or the Mississippi River, those have a very coarse textured soil. And as you go far away from that, which is just about a couple of 100 yards away, which is across this main road here, the soil becomes heavier or become clayey in nature. So with that differences in soil types or soil texture, definitely it calls for a different type of management practices that you're involved in, especially with tillage or any practice that will improve manageability of the soil during plowing. So with that, knowing the nitrogen is very difficult to manage, but it's yet very important nutrients to increase productivity, you have to consider that every field is different. There's no way we have to manage the field similarly because of these differences, as I've shown you in that previous slides where we usually cultivate our sugarcane. And so this is the reason why, among the reason why we ended up, putting into this effort is to find a better management for nitrogen fertilizer. Not only every field is different, but if you look at the within field variability, there's also possibility. This one I pulled from the satellite images that you can get through Google, and this is probably around the time where we pass about the grand growth stage, and it's pretty much at canopy closure. But what you can see here is that this field is not uniform. It may not be clear to most of you, but what you can see here is that those areas, those pockets of areas where I think the cane is thinner in terms of stance and less less vigorous as opposed to other spots. So you can see the possibility that within field there's variability that also exists, not only from field to field, but within field. And so my question is, if you are talking about with this field, are you going to invest the same amount of nitrogen fertilizer, the same investment that you're going to put in agricultural input for that matter on a place that will not deliver the same level of yield? And so this is the idea of why we're doing this, what you call a remote sensor, a variable rate application technology for nitrogen. Another example is this field that I took, and you can definitely guess where are those areas that are actually showing thin stand and likelihood that they're going to yield lesser than the rest of the field that is really lush and green. And so this is what I'm talking about, that when you manage nitrogen fertilizer, I would not invest the same amount of nitrogen to that place where I highlighted in yellow, just simply because I don't think they're going to deliver the same yield potential as the rest of the field. And if we have the capability to do that, why can't we do it? And this is another example because there's other way by which you can see variability in the field. And so this one I pulled out from the Web Soil Survey Circle, where you can get a map of the field based on soil type. And so this comes out to be a field that is fairly uniform. So what you can see here is just a field that has a two soil type. And if you don't see the second soil type, it's right actually here. It's a small portion of the field. So by looking at the soil here or the field from the top view image, you can say, oh, it's fairly uniform field to me. But when you look at the stand of the cane, and you just ignore this part here, okay, because we took the growers that we work on with this project, took this as a seeding material. But just focus on this area here. You can see definitely there's differences in the stand of cane. I don't see the reason why you have to apply uniform nitrogen fertilizer in a field that has different yield potential. So that's the point there. So what we did when I first came here in 2007, I took some data from the person who's running this from this response studies on nitrogen fertilizer. So what we did is we tried to look at this optimal nitrogen rate that we graph against year and the crop age, and we have variety as well. So what you will notice here is that when you talk about optimal nitrogen rate, this is the nitrogen rate that maximize cane tonnage and sugar yield. So what do you notice here in the graph that shows that year after year, depending on the stubble, depending on the cultivar that you're using, the nitrogen rate varies. And so there are years that you have about 40 pounds of nitrogen needed to optimize yield. There's several years that you need 80 pounds. And there's a couple of years that you need 120 pounds of nitrogen per acre to maximize the yield. But what's interesting is that there were years that we don't even need to apply nitrogen fertilizer. Okay, granted that I will not recommend no application, but at least applying the minimum amount to make sure we don't lose any yield if in case yield potential becomes much higher than what was expected in the later part of the season. But this graph tells you that we don't need to apply that much of a nitrogen year after year after year, 120 pounds in the same, uniform in the entire field. And imagine how much you can save on nitrogen fertilizer. Another way on looking at the differences in response to nitrogen fertilizer is what we graphed here. On the left, on the y-axis, you have the cane tonnage, and you have on the y-axis, we have two sites in St. Gabriel from 2007 to 2009 and 2010 to 2012. And in New Iberia, we have from 2010 to 2012. So the blue bar is the cane that received no nitrogen, and the red bars receive 80 pounds of nitrogen per acre. So those number on top of those stacks of bars are the cane tonnage in tons per acre increases due to the 80 pounds of nitrogen per acre added. So what you'll notice is this differences in increases. In plant cane, you don't see a lot, 0, 4 tons and 3 tons, but it doesn't mean that if it's a plant cane, it's certain that you don't get increases. You see here the per stubble in 2011, we didn't get any increase in cane tonnage due to the application of 80 pounds of nitrogen per acre. Where that you can notice is that we can have 14 tons increase in cane tonnage due to 80 pounds of nitrogen per acre application. But there will be years that it may only be 4 and it may only be 3. So what it tells you that, the response to nitrogen fertilizer, the yield potential of the crops or sugarcane for that matter varies from year to year and also in space. And when you talk about space, you're talking about field to field or within field variability. And this is how we fertilize excuse me, not how we fertilize sugarcane in Louisiana. So this is based from nitrogen response study that we've been conducted for many years, and so we have this averages, and we actually group them by plant cane, and then refine the recommendation based on soil, so light texture versus heavy texture. So on the third column, you'll see the nitrogen application rate, 60 to 80, 80 to 100, and so forth. And so the common fertilizer used, common fertilizer that we use here is the urea ammonium nitrate solutions that we inject on both shoulders, about 6 inches away from the center, and we knife that in. Sometimes we use dribble applicator, so we just drop the liquid fertilizer on top, and then we have an implement that covers it up to prevent it from volatilization or losses. And also facilitate mixes and contact between soil and the fertilizer. What is quite stands out with our fertilizer management, given the fact that I've shown you that variation in space and time exists in sugarcane production, is still, despite that fact, we apply nitrogen fertilizer in uniform rate. And so if in case we determine we're growing a stubble cane or ratoon cane on a heavy textured soil, we apply 120 pounds, and that will be the entire field will be receiving the same amount, regardless of the yield potential, regardless of the spot that may possibly have, there's a higher amount of nitrogen in the soil. So that's one of the limitation of our current fertilizer management system. And think about that on average in 2019, the nitrogen fertilizer cost for field operation for both stubble cane and plant cane is about 12.4% of the total cost that is you're putting in for operation costs in sugarcane production. That's a good amount of investment. And if there's a way that we can cut it down to so by using a more precise or accurate way of applying fertilizer nitrogen, why can't we do that? It's definitely worth pursuing that. So it's become my long-term goal, together with my team, to improve the nitrogen fertilizer management for most crop production system here in Louisiana, and that includes sugarcane. So what we intend to do here is to develop a better decision tool. I'm not saying whatever we have right now, what we're using is not working, but if we have a better tool that will guide us in making a more precise application method, it is an opportunity for us to increase income for producer and reduce these losses of nitrogen fertilizer to the environment. And so when we say develop a better decision tool, that means we will apply nitrogen on a need basis. And so what the plant needs or what the cane needs, we will apply to that. It's not going to be just based on historical information. And also with this technology, we're going to use the optical remote sensing technology. This is a way by which you can acquire information, not from the soil, but from the sugarcane itself. It's real time, it's fast, and we can get an instant recommendation. So with that, you get the reading and you can treat the apply the fertilizer on the go, as long as you partner or you combine this with this what you call variable rate applicator system, which will allow you to variably or selectively apply nitrogen fertilizer rates where it is needed in the field. So that's how it works. So fast forward with many years of work, this is the product that we're really looking at. It's now running in the field, and before we even run this, we had some performance evaluation tested done, and I'll show you some of the data that we utilized to make sure we're going to have more chances of success rather than just failure. So we did the performance evaluation a few years back. So when you look at this applicator here, you have this implement, and this is what you call a 5-row applicator in sugarcane. So essentially, we have the system, excuse me, installed here. We have 2 sensors that actually some are averaging the reading of the 5 rows. It's actually perpendicularly located, not perpendicular, in parallel to row number 2 and row number 4. Okay, we have that sensor that captures the sensor reading, and you have the computer that saves the sensor reading and convert that into application rate, and it also transmit that information to the flow meter and control bulb that actually regulate the amount of urea ammonium nitrate that will be dribbled using this drop nozzle. So there's 2 drop nozzle per rows, and it will be applied close to the shoulder of each bed, which is about 6 inches away from the middle. And for that, there's an implement, a coulter, that follows through, which essentially covers up the soil as soon as the nitrogen fertilizer is dribbled on the surface. So that's how our system works. So in a nutshell, it seems to be it sends what the cane needs and it applies right on the go. So it's a system that is working now. And so this is a different view of the system because that one is on the side view. So you'll be able to see what I'm talking about. Those 2 sensors that are located on the second row here, and it should be about 30 to 50 inches away from the canopy. And so you can see that sensor trying to collect the information. And as it goes, you can see how far along the sensor from the drop nozzle, being about a couple of feet away. And so you're wondering how fast the sensor can acquire those readings. And so I took at this just one slide to demonstrate and show to you what it looks like. And so the sensor head generates its own light, the red and the near infrared. And so as it generates those targeted crops, bounce back those reflection that either absorb or reflected back. And that converted into what you call this NDVI reading. So the definition of NDVI is Normalized Difference Vegetation Index. It is an information that tells you how green the biomass is and how big the biomass is. So essentially the values range from 0.1 to 1, and as it approaches the values of 1, that means you have bigger and greener plants, and that means a healthier plants, and that means it has a good nitrogen supply soil, and that bringing a very good stand of sugarcane. So the sensor field of view is about 24 inches wide, and the thickness is about 0.4 inch, and this is where the output is. With that, the sensor readings for every second take about 1,000 measurements. It averages in that little input that is about 10 readings in this input. So you're probably going to see about 10 readings in this field of view, but that is actually an average of about thousands reading. And so that's how fast it is, which makes it suitable to do a variable rate applicator on the go. So it's a sensor that tells you what nutrient status or nitrogen status the cane is, and that translates into a recommendation. And so even if it sounded so easy, that recommendation has required a lot of effort because you need to build that algorithm that computes it, convert all the sensor readings into nitrogen recommendation. And just to touch base also on, if you see that tractor with the equipped with the sensor, with the computer interface and so forth, how do we determine using that system, the nitrogen rate applicator? Like I told you, there's an algorithm that involved, and maybe it will take a long time for me to explain, but this is how we foresee the value of using remote sensor readings, or what you call NDVI, as our estimates. So if you look at the first column here, you see those N rate variables. These are the variables that are typically used by researcher to get a recommendation for a nitrogen fertilizer. The first one is crop yield, and crop yield tells you about the nitrogen demand. If you know the demand, then you'll be able to know what rate of nitrogen fertilizer you have to apply to meet that demand. Now, the next question is, of course, there are nitrogen in the soil, and we can actually account for that. There are laboratories or institutions that actually test for soil nitrogen, and in some places it works, but it doesn't work here in Louisiana because we have a high and average annual rainfall, and so we pretty much not going to have a long-term perspective of nitrogen availability. So what we measure today is just a snapshot information of nitrate and ammonium, and the next day we get rainfall, that value will be different. So it's not going to be a long-term perspective of availability of soil nitrogen, but testing will do. So if you know the demand and you know what's in the soil, then you can subtract what is available from the soil, and then you can have the nitrogen recommendation. One thing that is quite tricky when you're dealing with quantifying available soil nitrogen, there could be many sources, and it could be differ from one farming system to another. We have organic matter mineralization. What you have in day 1 may be different from day 200, which is may fall from the time that the crop in question or sugarcane is actively taking up nitrogen. So there will be residual in those remaining from last year. Fertilization, there's also atmospheric deposition. Rainfall can bring in a diluted form of nitric acid, which also has some nitrogen in it, and some of those particulates containing ammonium that will go back to the earth that itself are available nitrogen for plant use. And like I said, farming system, if cane is rotated with soybean, that could have a credit for nitrogen. Or if there would be farmers or growers who uses manure that also adding nitrogen to the system. So these are information that we need. So what we look at the second column tells about how can we get those information using the remote sensor. So this is how we use the remote sensor. For example, the yield potential. We were going to estimate the yield potential using this established relationship between NDVI or sensor reading with cane tonnage. This is just a simple linear relation, not linear, but an X and Y relationship between these two variables. So with years and years of work, and this is just, I think, a couple of years of data that we have. And so you can see you can imagine how much stronger the data that we have now, how robust the database we have, because we've been collecting data year after year. So we have that particular relationship between NDVI and cane yield. So if that applicator that I showed you in a few slides ago collect the NDVI reading, it tells you what kind of yield potential we're expecting for cane yield. Now we have an estimate of end demand. Now the next thing that we were doing is to include this what you call enriched strip technology. So 21 days before the expected fertilization of producer, we will put out this enriched strip in the field. And so what you see here in the diagram is Mr. Keith Dugas on his right. You will see the enriched strip, which is definitely greener than the rest of the field. The rest of the field is going to be scheduled for nitrogen fertilizer 21 days after the enriched strip was established. So you can see that there's a difference, okay? The one on the enriched strips, canes are are actually greener compared to the rest. Now, your eyes can visibly tell the difference between the two. But what the sensor tells you, what the sensor can do for you is to convert these visual differences into numbers, okay? And that, again, is an equivalent information about what is available in the soil. So, for example, now in the photos that you see here, you can see that the enriched strip is greener. So what does that mean? If the enriched strip is popping out so clearly in the field when the day of fertilization arrives, you can tell that there's not much nitrogen in the soil. Why? Because that enriched strip, which receives 120 pounds 21 days prior, are growing much better than the rest of the field. So the rest of the field is just saying that, hey, we need nitrogen fertilizer here because that enriched strip is showing a very stand of sugarcane. So that's how we use this enriched strip technologies to tell us whether we have this available soil of nitrogen in the soil without soil testing, okay? So you can see how instant the information you can get. And then, of course, when you have your soil tested, imagine how much time you need to spend with collection of soil sample, how many soil samples that you have to collect, and then how much time or how many days that you have to get, or the turnaround time to get the samples, the results from the analysis, bringing it to the lab and getting the results from it. So it takes a long time. But here it's just converted into NDVI reading. So how do we do that? So this is one example, and you can see here, the y-axis, you have the NDVI reading, and on the x-axis, you have this degree of plant coverage. And so from the left to the right, you see it's becoming greener, right? So with that information, you can see the NDVI reading increases as the plant coverage getting greener, and you barely see some grounds in the background, okay? So how do we use it for enriched strip or estimating of soil nitrogen from the soil? Is assuming this is the target area, the first squares that appear in the PowerPoint, and the enriched strip is in this area. And obviously, because it received more nitrogen than the one on the left square, that is greener. So what if you have that NDVI, translate that into reading? That differences in NDVI is one information we use to get the recommendation out. So like I said, it takes a long time before we generate the algorithm, but at last we have the system running. And I have a couple of slides showing what it looks like. You see here on the left, you see that a screen showing the progress of the application of the fertilizer. And by the way, it maps out the NDVI reading, it maps out the fertilizer that you apply. And at the harvest, we have the yield monitor that map out also the yield. And you can see here this sensor on top of row number 4. And this is a different applicator where we have only one that injects nitrogen in the middle portion of the row. But still, it based on that sensor reading that it collects and then apply nitrogen fertilizer on the go. So that's how it works now. And so you can see from the screen, which was shown earlier, how much nitrogen is being applied. You can see that on this upper right corner, 24 gallons, that's equivalent to the urea ammonium nitrate solution that is actually applied. So that's how it works. Now we have another unit here. This is more of the prototype, where we have this spider with a high clearance applicator system. You have that UAN at the back. There's a big container at the back of the spider, and you have that 2 sensors again. But this is 3 rows at the time. You can see the Y drop having 2 areas on the top of the bed that is dribbling nitrogen or urea ammonium nitrate solution. So that's one way we have this sensor system working. So with that, you won't see a field that receive a uniform N application. This is what it looks like. Like I mentioned, we have ways by which we can map the NDVI reading, and this is one block of the field with Mr. Keith Dugas. I think this is about a 10-15 acre field. So you can see differences in NDVI reading. Because the sensor detected these differences in NDVI reading, it calls for different application of nitrogen fertilizer. And so we have that differences in application rate ranging from 41 pounds to 133 pounds. It's not like when you say save and you may be wondering, oh, wait, we apply 133 pounds, where in fact the highest application rate and uniform amount is 120. Well, that's the beauty of this application system, of this system, where we have possibly this part of the field may yield more if we put down more nitrogen fertilizer. And the next slide will tells you so about that. So on average, when you look at this whole block here, it's about 85 pounds of nitrogen per acres. If the producer apply 120 pounds of nitrogen fertilizer, it will apply 120 pounds uniform. You can imagine it's just, what's the point of applying 120 pounds in those red areas that only may need about 40 to 60 pounds of nitrogen fertilizer? Now, there are fields that requires more than 120 pounds, but it receive 120 pounds. And so that is where we've seen the precision or the accuracy of this method of application, where we can apply the amount of nitrogen that the cane called for. And so the yield tells you a lot too, that there are differences in many places of that same field, different levels of yield in cane tonnage, ranging from 22 tons per acre to 68 tons per acre in yield. And so this is the yield monitored map that we obtained for, I think that was last year harvest. So you can see the differences in yield. So again, we're going to talk about why do we have to apply uniform application rate when in fact there's differences in the demand of nitrogen fertilizer. There's differences in the soil potential to supply nitrogen. So we have to account all of those, and that increases our fertilizer use efficiency. Like I promised, we did the performance evaluation of this technology on 3 sites. The plot size for these 3 locations in Louisiana is about an acre field. That's pretty good size per plot, and it's a well-replicated field. And so you have several columns here under 2013, 14, and 15, and each of those years you have the data and applied, and then the sugar yield. And we will break down how we will analyze whether we get a net return much higher than the farmer standard practice. So, for example, in Dugas site, you have the farmer standard and practice and the sensor VRT nitrogen management system. In 2013, so what you will notice is that he applied 100 pounds of it, and his call, with this rate, it's still called, but the difference is that he applied it in uniform, as opposed to the 110 pounds per acre. You see that it doesn't mean that there's a lower recommendation rate, but because the sensor detected a higher yield potential, that results to a higher application rate than what was the farmer standard called for. But look at the yield return. It ranges, it's about 300 pounds more of sugar per acre. And so what you'll notice for the rest of the data, it's more common to see that the sensor base is recommending lesser amount of nitrogen fertilizer that the farmer standard did, except for this one. And that there's not much change. If there is lesser amount of fertilizer applied, it did not result to significant losses in yield. And so the savings incurred, or the savings that made from applying nitrogen fertilizer at a lower rate, offset that small losses in yield. And so when you look at the summary here, we have the 3 site, Douglas, Gravois, and the Sugar Research Station, and that we use the price of the sugar at 22 cents a pound, and the price of nitrogen fertilizer at 65 cents a pound. So in those 3 years, totaling up to complete the whole cropping cycle, the sensor-based nitrogen recommendation ended up a positive return or higher return, as much as $315 per acre for the 3 years of harvesting. And so for Dugas, it's about $156 and $27 at the Sugar Research Station. I have to explain why there is a negative value here. I'm not giving an excuse, but this is something worthwhile to mention, that the reason why there's a negative return is that when we fertilize, because like I said, the nitrogen, the sensor-based VRT application system is applied 21 days later than the farmer standard practice. By the time when we apply the sensor-based VRT recommendation, the next day we got about 5-6 inches of rain, and so essentially we lost what we applied, and we never get the chance to get back to the field to do a reapplication if it's for the purpose of continuing the performance evaluation. For a couple of reasons, it didn't get dry enough for us to get in, to get the fertilizer in time. And second is, how are we going to treat this? We apply the fertilizer already, and so we are going to have a double application rate. So either way, we ended up not going back there. But the good story is that when you're looking at the whole cycle of the sugarcane production, we ended up having a net positive return compared to if we use farmer standard practice as a reference. Keep in mind that this is the fertilizer cost. If this is a practice or a technology that a grower should be adopting, there should be investment on the sensor and the use of the computer or possibly the software. It may not be costly because the most I would say the most costly among them would be the variable rate system, which I think most of the producer, and they have the GPS, guidance already. So I'm pretty much sure there's nothing much investment that needs for those components. But if you look at let's break it down when it comes to nitrogen applied and the yield. So in Dugas site, we have a 18% reduction in nitrogen fertilizer, and we didn't lose yield. In fact, we increased the sugar yield by 3%. Same story with Grabois site. The reduction in nitrogen fertilizer is almost half. It's 41%. So you can imagine how much savings on investment you are on putting away for nitrogen fertilizer, but then it didn't cause any yield reduction. In fact, it increased by 5%. That's for among the three sites. That's the highest return, total return that you can see. It's about $315 per acre. At the Sugar Research Station, there's a reduction of almost 14 or 50% in nitrogen applied, and there's a slight reduction in yield, about 1.4%. And like I said, even if there is a slight reduction, the end up total return is positive simply because the savings from nitrogen fertilizer offset that losses in yield. And so this definitely gives you an idea how the system works. So I have a few more slides remaining here just to show you where we at or where we stand right now, because the technologies just keep on progressing and it's just hard to keep up. Now we were using also what you call this aerial images that is taken by a camera equipped or attached to a unmanned aircraft vehicle or drone, as shown in the photos here. And so we want to generate an end prescription maps. Nothing different on this, because those images that we stitch together to get the map is geo-reference, so you can go back and use that as a way by which you can, as a guide for you to apply nitrogen fertilizer. It's a very, in terms of advantages, like I said, the coverage is larger in a short period of time. You can fly a drone and get several hundreds acre compared to the ground-based sensor that we have now. But then it's something to have to understand that these two this system is a different platform as to what we're using in our on-the-go sensor-based BRT system. There's challenges. There are challenges that are actually presenting us. Like, for example, we need to calibrate it. We need to make sure that what the ground-based sensor is the same as what the camera is seeing, and that will cut us a lot of work when in terms to converting those readings into nitrogen recommendation. Another thing too is that the sensor is, most of them, as far as I understand it, there are still passive sensor. There should be, which means that there should be a certain time of the day that you can fly the drone. So if it's a cloudy day, you don't want to go out and take images. So it's really dependent on the light source, the light source being the sun. So if it's the angle is different, so you might have a different value. So it's very critical that you pay attention on these details when you use a sensor similar to what we attach to camera to our drone. But like I said, there could be other sensor now that is what you call active, just like those ground-based sensor, the green seeker that we're using, that you can use and utilize the same information for the same purpose. But it's amazing how, like I said, this is a diagram, a field that we have different nitrogen rates. So you can see that as you fly, you can see that plots where we have no nitrogen application made on, so they're very yellow, and that can be captured in the images. And as you process, stitching together those images and converting that into NDVI readings, definitely there will be association with what the green seeker or the ground-based sensor can pick up versus the one that the sensor, that the images derived NDVI can actually measure as well. So this is just one example of the flights that we have where we could definitely clearly see the difference among plots. So one also, I would say, we encountered this problem because the high resolution of the images that we've taken using the camera we're using was different from what we're using right now. It's high resolution, so there's too much detail as seen in this diagram here. And so we have to process it to a way where we can categorize it into a much, I would say, lower resolution. So grouping them into 4 or 5 instead of having those too many information that is quite hard to follow through. So I think we've overcome this challenge, and I think something but worth mentioning in this presentation. So just to give you an idea, this is again another field where we flew in. We have that on top view. We have the the RGB photo here where you see those with the arrows. These are the enriched strip areas. So you can see those are greener compared to the rest of the field. So it just tells you the rest of the field needs nitrogen fertilizer. That's where we have the sensor. VRT system will tell you how much, and they can do the job in applying, the rate that is needed, where it is needed in the field. And the UAV aerial images capture that information. You can see that same arrows that show that greener areas, and that's the enriched strip. And so it just tells you, and this is the NDVI map that we got, and this area here is where you have the enriched strip showing also higher NDVI reading. The dark, I would say that purple color is the highest NDVI reading. So there's definitely agreement, and that's where we work on, just to make sure if we are to use the algorithm where we can generate the nitrogen recommendation from the VRT sensor on the go, so we can have also the prescription maps. We want to make sure that these two platforms, the ground-based sensor and this camera, are seeing the same thing, at least things that can be compared. And if not, we should have a correction factor if in case we want to use the algorithm for nitrogen recommendation. So Bruno, with that, I think I'm going to end my presentation. Definitely, I've eaten more than 20 or 30 minutes that you allotted for my presentation, but I do thank you for your patience, and I'll be more than happy to answer any questions that you may have. Thank you.
Okay, thank you so much, Dr. Tubana, for our presentation. It was really great. Now we are going to open for a few questions. And you can stop your screen sharing, Doctor. Okay.
So it's working now.
Yes.
I was presenting blind. I don't know.
That's okay. It was really good. So let's see if someone have a question, please. you can send to us right now. Let's see on the comments.
Well, I see JV saying congratulations. Did I pass the exam?
Daniel, he's here too. Yeah, he said go Tigers. Okay, we have here, let's see, Marlon. He's asking.
So do you want me to read the question?
Oh, I can read. What is the
Yeah,
biggest
okay.
challenge in
Yeah.
using a remote sensor to apply nitrogen in sugarcane? And is it the cost of implementing these technologies high?
Okay, so the first question, the biggest challenge. Of course, I would say the biggest challenge is that you need ample time to get the database groomed, or you have to collect years and years of data to get establish this yield potential predictive equation. So everything that we have and estimates that runs the computer and tells you what needs to be applied, this is composed of algorithms that requires big data, and that requires a good amount of time and numbers of trials that you have to collect the data from. Is that normal? Yes, it's normal. I mean, everything has to be normal. I mean, with the soil test recommendation for those who using it for, in places in the United States, that decades of work. So I think that's one it. But then once you have that, it's actually pretty stable. Even if we have recent addition, like I said, we've been updating it. We still continue to put more data points. It doesn't change the equation at all. If it does, it's very minimal, and it's not that something that will change the recommendation from 10 to 40 pounds per acre. Okay. And the next question is asking is the cost of implementing these technologies is high? Uh, I would say fair amount, because I think precision ag has taken off. You know, I would say it has taken off a lot of time already, and there are a lot of producers, most of them who's using already some precision technologies. That all they need to do is to add the sensor if they don't have any. And again, and the cost of that is not as much if as what you expect from buying variable rate, a tractor, many sensors and computer softwares. And one thing I would need to emphasize is that if the sensor for that unit that I've shown you with 2 sensors, that's about, give and take, you're paying about $8,000 for 2 units, plus some software, assuming the producer had the VRT system running already. GPS not a problem. You have also other things already in place. Look at the let's take, for example, Keith Dugas's return in one in on average for trees is $156 per acre total for 3 years divided by 3. So per year you're paying you're getting an extra $50 per acre. If you're farming 2,000 acre fields, you do the math, then you almost pay off for the sensors and softwares that you already bought. So that's only the first year. It could be really rewarding the first and second year of adopting this technology.
Okay, let's see. We have here, what gains can this technology provide?
Oh, this is a very big question. A lot. Now, this is how we can break it down, because I noted about the problem we're having with mismanagement of nitrogen fertilizer. If you over apply, if unnecessary amount of nitrogen is applied to your cane, so first thing you're going to lose, that investment is not going back to the producer, right? So economically speaking, you lost some money in there. Second, excessive amount of nitrogen excessive amount of application of nitrogen can result to yield losses as well, especially for sugarcane. You don't want to apply too much because it results to reduction of sucrose content in the stock. And the third one is those excessive amount of nitrogen fertilizer that were not utilized by cane is going to sit there, or probably just got lost from the soil system. And those are, I said, like I mentioned in those few slides that I mentioned, the consequences of mismanagement of nitrogen fertilizer, leading to increases in concentration of nitrous oxide in the atmosphere, and results to algal bloom and this what you call dead zone, so enrichment of nearby bodies of water. And so that causes this hypoxia region, this place in this water losing its oxygen simply because of the consumption of microorganism that utilizing the algal that actually the growth has been in excess, and then they die and microorganisms utilize it, and so that marine ecosystem is generally impaired. If I remember it right, in Louisiana we have this fisheries that is mostly affected by this hypoxia region. So instead of those marine life that can move, imagine fish that move away, and so those fishermen that has to go and go further from what they usually get their fish from. They're going to spend more time and fuel just to get the same or catch the same volume of fish. And so that's just a big umbrella of effect. I mean, and like I said, the gain, you talk about the gain, all of this that I mentioned will definitely be in what do you call this, the effect of using the technology, reducing the amount of nitrogen loss in the environment, better income, and then yield is going to be secured because you're just applying what the cane needs. Okay, so I hope that I got that answered.
Okay, we have last one from Mr. Dugas.
Take it.
He's here. Thank you so much, Mr. Dugas. Trimble RTK system is compatible with the green seeker technology.
I don't know if it's a comment or not. I don't know it's a compatible. I think green seeker technology can work in many systems. It's just it's a learning curve. Maybe that's not my forte, but definitely it's gonna work with the RTK system.
Okay. So thank you so much. It was a great pleasure to have you here, Dr. Tubana, with
Well,
us
the
today.
pleasure is mine too. I'm glad that I was able to connect. I mean, I've been in your place. I've been in the university, and it's a wonderful place. And I wish I can go back and spend more time again and be able to talk about more of this technology, because right now it just took off, and with Keith, and I'm glad Keith's listening. And this is something that definitely a significant event that took place in a couple of years, and it's already in the field operating system. He's now, I would say, more of an expert to say that he's very proficient in using the technology. And all we did with my grad students, with you, Bruno, is having the science ready for producer to use this technology.
Okay, I also want to thank everyone here today in our live discussion. It was really good. And after our live, I will post this video on our YouTube channel. Okay, so please, guys, share this video and have a great night. Thank you so much.
Thank you
Bye.
so much. Have a great evening, everyone, or have a great day in other parts of the world. But all right.